Good evening, everyone. So we'll start at 7:05, and those who are here now, if you have any doubt or anything you want to know, you can message me or just say it here also. Okay, so I will start, huh? People will come and then I have to admit, anyway, nothing can be done. Let me share my entire screen. There I go and share. Anyone can type in the chat box so that the screen is visible or not. Hello, am I audible or my screen is visible? Yeah, thank you, Viva. So, yeah, thank you, Sabah. Let's go ahead. We don't have much questions, very simple, and I hope I will cover it in within 1 hour. Hmm. So, good evening, everyone. Again, NPTEL-Day3, Reaction Mechanism in Organic Chemistry. You are aware of it. And I'm again Manojit Das. So, we'll talk about some questions on kinetics and some question on Curtin-Hammett principle. Yes, these two topics are there, and yes, I knew it. That's why I didn't start. Anyone else? Okay, so let's go ahead. This. So introduction is over. Let's start with the question. So this is a simple question, and I would say this question can be even asked in class 12th standard or BC standard also. It's a pretty simple one. So we are given an equation, multiple steps of a reaction. Let's say we start with reactant A plus B, which is in equilibrium with C. Then after C can form, it can go to D with rate constant of K2. D then with the rate constant of K3 can um, yield two product E and F. So it's a simple, I won't say simple, it's not a simple reaction, it's a hypothetical reaction. It may happen. Can we write the rate expression for the successive steps? So for example, what will be the rate expression for the first step? What will be the rate expression for the second step? And what will be the rate expression for the third step? So that's we are going to show. And it's very easy, and I will just write the steps equation. So before I go there, I need again our tool. Tool is here, whiteboard, open a jam, start a new whiteboard. Yeah, perfect. Well, it's come, share with people. Yeah, continue. Just a second. Hmm. Nice. So let me give it a two thing. So I will write it this side. So I have A plus B, and then which is an equilibrium with C. Forward rate constant is small k1 and the reverse rate constant is minus k minus 1. Okay, these are small k. So if I want to write rate expression for this step only, so rate, if I want to write rate equal to k1 into concentration of A into concentration of B, right? Then since it is going back to the C Un's form, it can it can stay in equilibrium with A plus B. So we'll have minus K inverse concentration of C. So this is the first expression. Okay. So this was the case here. It is very simple here. And then if we look for the second step, which I will write it here with a different color, let's say, which is forming D. So what will be the rate expression here? And just let's just put that rate 1 here and then rate 2. Okay, I'm writing it here. Okay, rate 2. What will be the rate expression here? Since we have rate constant given as small k and then 2 substitute, so it will be k2 and then concentration of C, right? So this will be the second equation. And what will be the third equation? I will write it here, R3. What is the product here? So basically it doesn't matter right now here. So we are starting with a single E plus F. So it will be R3 equal to, and it is given K3. So it will be K3 into concentration of D. So overall these three are expected here within this question. Can we write the rate expression for the successive steps? So these three are asked here. Okay. So it was a very simple question. That's why I don't discuss that much here. Now let's go to a second question, which is also very simple. Now this question, we are given a addition reaction. So one second. Okay. So we are given a addition reaction where an alkene and in HCl is getting added here, alkene, and then forms this fluorinated hydrocarbon. Okay. For the above addition reaction, the rate was found to be rate equals to rate constant, concentration of this alkene, concentration of HCl to the power 2. Question is very simple. How will the plot of the rate of product formation versus reactant concentration will look like? Remember, when we draw such plots, we are assuming that one of the reactant is in high concentration, so overall it doesn't affect the other. So how will you do that? Let's see. So again, I will make it like this and clear the frame. So simple. So I will write it as A plus B, where A is the alkene and B is the HCl, and then product P. P is the fluorinated hydrocarbon. So if I assume this reaction and the rate is given as R equals to rate constant K, alkene which I have considered as A, so it's like this, and then HCl which is considered as B, so B concentration to the power 2. This is the experimental observation. So they have asked, so I will draw within a single plot x versus y two curve. Okay, so if I say this is rate of product formation dp by dt, and then uh, this will be concentration term for the each species. So for A, it's a first order reaction. So what we expect, a straight line passing uh, through here. And what is the case for B? It will be a second order reaction. So it will have a y equal to x square like a plot. It may be like this, or it can be little, the slope can be different, right? So overall it represent the this reaction, the rate equal to K into alkene into HCl square. So this will be the case. And other thing is possible also, like it can pass through, I mean here also like this, and so we are assuming it here. Overall this is the case. How will the plot of rate of product formation versus reactant concentration will look like? Okay, now I will look into a little big question which I will be discussing. It will just take little time. Okay, I'll give you some time to read the question. There are a couple of things that are noted here. So give a plausible reaction mechanism for the following reaction. Hmm. So we have uh, benzaldehyde, hmm, and then it is reacting with PHCOCH3 in presence of ETONA or ETO minus. It is forming this one coupling product, and then it is undergoing dehydration to give this alkene. So from the postulated mechanism, can we develop? So first it is asking, give a plausible reaction mechanism for the following reaction, which we will first show. Then from the postulated mechanism, can we develop a kinetic expression matching with the experimental observation? So what is the experimental observation? Experimental studies of this condensation reaction have revealed that it is third order. Just a second. So what I am showing here, it's a third order reaction. Third order reaction, what will be the rate? That is what we seek actually, and also from the based on the reaction mechanism we will try to answer these things. So first I will show the reaction mechanism step by step, then we will analyze each step, what will be the then what is the rate determining step that is we want to find. So just it will just will take time. Please stay and try to follow, please. So I have PHCHO first, so I will write it as PHCHO plus I have PHCOCH3, which in presence of base, that is we have considered ETO minus, what is forming PHCOH CH2 CO and then pH. So this is the initial product which undergo dehydration to give us pH alkene CO pH. So this is the reaction. Now there will be a lot of things. Anyway, I will try to show you here. So first we will try to get the mechanism, which is very easy. So I don't think I can show all these things here. So anyway, I will try. So what will happen first? This PHCOCH3. So PHCOCH3. In presence of base, it will undergo deprotonation, that is ETO minus. Will abstract one hydrogen from CH3 to form the, so this as an acid, so the conjugate base CH2 minus, right? CH2 minus. You can draw the corresponding canonical structure also. Plus ETOH. Remember, solvent is ethanol, so it will be in high concentration. So I will need several points. One second. Admit. So this Jamboard is not sufficient. I will show it in camera. Okay. So it is better here. Please stay with this. It will just take little time. So I will step by step on. But I'll show pH. Sorry, PHCOH. It is our one reactant, and then plus we have PHCOCH3, right? And we have the product. So what I in the first step I shown. First step I have shown. So PHCOCH3 and then plus ETO minus. Sorry, minus. So this one, and then what I have is simple, because I need to show all the things. That's why I'm coming here. CH2 and then minus, which I can get it from here. And then plus ethanol. First step is done. What will be the second step? Second step is the coupling. Coupling, this anion PHCOCH2 minus will attack this PHCHO, which I can show like this. I will try to show it here. CHO, then plus what will happen? CH2, and then I have a minus, right? Control Z. I need this minus to be here. Okay, no problem. This will two form will react. We have one friend to admit. So what will happen here? It will undergo and then it will form our intermediate, right? So I will show it here like this. CHO, there will be OH and CH2 COPH. Just a second. So I have here, it will be O minus, remember, and then this will be ketone, and we have pH here. So this is the case. Let me show it here. Now actually what happened, these are in equilibrium. Okay, so I will show this kind of arrows, and I will show the corresponding rate constant. So I will put it at K1, and then another I will put at the lower side as K minus 1, and then if I put it as K2, and I will put at K minus 2. What will be the third step? Third step is the this anion will get just acid base reaction, one simple reaction. So if I take this, Control C, Control D. So remember, this is the third step, and it will be a simple reaction where our reactant is ethanol, ETOH, and what we expect is this Control V, and then we have not this O minus now. All we have is OH. Perfect. And what will be the fourth step? In the fourth step, this will undergo dehydration. That is, again we'll have ETO minus, right? So I didn't show it here, but it will be here, plus ETO, and then our favorite sign here, ETO minus. So then Let me get it here back. Control C, Control V. So this will be mainly just some equation solving. Okay. Again, I will have the equilibria signs and other things as usual. And what is our product? To get the product, I just need this simple thing. Control C. Yeah. Okay. So our water won't be there, but it will be a double bond. Sorry. Just a second. I can get the double bond here. So this is the product. Now I also need the rate constants here. So K3 and then K minus 3 and then I have K4 here, right? So just a second. Yeah, so these equations is not represented by this. Perfect. Now we can do one thing. So this is the overall mechanism. Okay, just a second. Admit. So this is a little bit complicated. It will be clear. I mean, I hope you are getting. If you have any question, just write it in the chat box. Now we are going in some other direction, not typical organic things here, though it's organic reaction mechanism. Now, so we don't know the currently the rate expression, right? Rate expression, which is the rate determining step, that is our target. So we will assume different thing. So imagine first case, situation 1, or that K1 is the rate determining step. So we are assuming that K1 is the rate determining. This first step is the rate determining step. And if we assume that, then our rate will be, so remember case 1 I am discussing. Case 1, first step is the rate determining step. First step is the rate determining step. If it is the case 1 first, so what will be the rate? Our rate will be, should I try? Okay, right, equals to, it will be K1 into concentration of our, pH, CO, CH3, concentration of this, okay, this, and then into concentration of ETO minus ETO. I'm just putting minus here, I hope it is visible. So this will be our rate expression if we consider the first. Let me change the color. Okay. Now we will ask the second question. Can the second step can be the rate determining step? Can be the third step is the rate determining step? What about the fourth step? Now we can easily eliminate the step 3, which is this 1, 2, 3. This part. Okay. This part. Why? This is a simple proton transfer step. So this will be very fast. So this equilibrium will be very fast. So ethanol to this O minus is getting protonated, right? So this is a very fast. So it cannot be the rate determining step. So we will cancel this step. Now we'll come to the what about the second step? What will be the second step? And if it is the rate determining step, so we will assume case 2 where second step is is the RDS, rate determining step. This is the situation. So again we can write our equation, but it will be little anyway I can write it, no problem. So our rate will be this time K2 into concentration of pH CHO, and then concentration of pH COCH2 minus, we have one sign. So this is the case. And now what happened, this pH CHCO2 minus, we want to replace this concentration with some other terms. Okay, now you can understand this from this first step, what is the equilibrium constant? So equilibrium constant capital K will be equal to concentration of product, so that is will be pH COCH2 minus, since ETOH is in ETOH is solvent, its concentration is large, so it is independent of that, divided by concentration of the two reactant, right? So pH CO CH3, right, and multiplied by ETO minus. This is the case. Now if we get the concentration of PHCOCH2 minus, our expression would be, so concentration of PHCOCH2 minus concentration is equal to capital K. I should name is capital K1. Okay, equilibrium constant 1, K1 into PHCOCH3 and into ETO minus. So this is the concentration of PHCOCH2 minus. Now if I replace this concentration of PHCOCH2 with this part, our rate will be, I can come here, I can write rate equals to equilibrium constant, rate constant K2, PHCHO remains as it is, and then in place of this I will write K1, capital K1 into concentration of PHCOCH3 concentration, and then ETO minus, which is just a second here. So overall we got this as a rate expression. If we consider case 2, second step is the rate determining step. Let me change the color so it will be good. So here let me rewrite it. For rate equals to, and K2 into K1 will be another constant, let's say K double prime or single prime, into concentration of the other things. So three things, concentration C, and I will remove this. So overall from this second step we can see that this reaction is third order, first order with respect to PHCHO, first order with respect to PHCOCH3, and first order with respect to the base ETO minus. So it's a third order reaction if we consider the case 2. And again we have considered that this is the fast proton transfer step, so it is not the rate determining step. Now what about the K4? Now we'll consider another case, that is case 3. Now this time it becomes little lengthy and big, but anyway I will try to show it. Okay, please stay with. So now rate will be here, rate will be what, you know that rate constant K4 into concentration of this how do I say, this is the intermediate, one intermediate. So let me rename something. So I will put name here. Okay, I will put it label as I, capital I, control C, make it bold. So this is I, our intermediate, and similarly we have I here also, and we can consider this as I minus. So I minus, sorry. So I minus, which is reacting with ETOH to give I only reacting with ETO minus again to dehydration, this part plus OH minus. I didn't show actually here. Okay, so there will be plus ETOH, and then plus what will happen, OH minus. So these are also there anyway. So if I write K4 rate for this case 3, what do we have, K4 into concentration of I into concentration of ETO minus, right? Now I have to do multiple step, which I am not okay, I can show it, it's not a big deal. So basically what I want is, I want to replace this concentration of I with the concentration of known reactant. Okay, who is there? Sorry. Okay, thank you for people staying, 14 people. Okay, so again I am saying my goal is replace this concentration of I with the concentration of known reagent which we can measure. Now who is joining? Okay, Gopika, please try to join little earlier. Okay, no problem. And this, so I just told the goal. Now how do I get the concentration of I? So I is our intermediate, this one. Now what I will do, from this step, this third step, I will get the equilibrium constant. So what will be the equilibrium constant? Let's write it in the right side. Capital K equilibrium constant equal to, we will have concentration of I, and then concentration of ETO minus, right, divided by concentration of I reactant side, concentration of ETOH, which is in excess amount, so I won't bother about it. I missed something, right? I, and then this is I minus. This is I minus. So these are all very small, I think. Control A. Just a second. So this is much more clear, and then I can increase the size as well, right? Where should I go? There I go. Just a second. So this we have. Now what will be the concentration of I minus here? Now let me write it here. Admit. I hope this is not too lengthy, but anyway, I thought to discuss it. Concentration of I minus will be, what will happen? It is in I, K3 will be. So let me check. Equilibrium constant, I will be off, and then it will be below. That's what I into ETO minus, and then I into, just a second, ETOH. Perfect. So concentration of I will be, so K3 will be just below, right? I think I'm okay. Perfect. And then ETO minus, and then divided by K3. That's what I was thinking. So I need concentration of I, not I minus. So concentration of I will be equal to, I remains as it is. So K3 into I minus will come. K3 multiplied by I minus, and this will be divided by ETO minus concentration. Yes, perfect. So now I will replace this here. Concentration of I. So what will happen? Rate as usual. I have K4. Sorry, and then concentration of I in I will be. So I have equilibrium constant K3, concentration of I minus, and then since ETO minus is above and then ETO minus will be below, so it will just get cancelled out. Okay, so all we have is I minus. I hope this is clear. So we are at this point. Now it is not till solved, so I need concentration of I minus. So concentration of I minus, how will I get it? Again I have to, will come from the second equilibrium, which is K2. So K2 equilibrium constant will be, again product side I have I minus this time. So I minus, and then divided by, in product side what, reactant side what I have, PHCHO and PHCO CH2 minus. So PHCHO and then PHCO CH2 minus, these I have. So from here I can get the concentration of I minus. So I minus, it will be, it's just simple, K2 into concentration of PHCHO, concentration of, sorry, PHCOCH2 minus. This is the situation. And we also know that if you see, look closely here, this part, concentration of PHCOCH2 minus can be replaced with this PHCOCH3 and ETO minus. So that I will do here. Just stay there. We are very close actually, please. So I'm solving in front of you. So basically I'm doing it by my own. That this hydrogen should be small letter. Okay, sorry. Then PHCHO, it will be as it is. In place of PHCOCH2 minus, I am writing this. So I have K1, sorry, K1 into PHCOCH3 multiplied by ETO minus. So ETO minus. So that's what we have here. So I will copy this part, Control C, and I will place it here. Remember, here we were, right? Rate equals to, then K4 multiplied by capital K3 into, in place of that, Control V. So now it makes a little more clear. So again, rate will be, I will all this put together, the constants K double prime into concentration of PHCHO, concentration of PHCOCH3, and concentration of ETO minus. Now comes little problem. What is the problem? Again we came to the same expression. See the red color here, we had a third order rate equation, right? 1, 2, 3. Here also, if we consider the case 3, I mean meaning that the last step is also the, can be the rate determining step, and it is follows the third order kinetics. So let me color it. Sorry, just a second. Just a second. Yes. So if I give it as a green color, let's say. That's not a good choice. So the what is the problem? Problem is that case 2, where second is the RDS. We can also have third order equation here. And if you consider the K4 also, I can also get to the similar expression. Now the question is, which is the rate determining step? So here I will read, actually this example is from Carey-Sandburg book. So we determine the rate equation. So it is first order with respect to all the three components, PHCHO, PHCOCH3 and ETO minus. Now the question is, which is the rate determining step, whether it is the second step or is the fourth step. I hope you got the mechanism, how do we get to the equation. Now I will read something from the book which will make it clear, and you just follow the reaction mechanism here. So if you follow it, so experimental studies of this base catalyzed condensation, so it's a base catalyzed condensation, have revealed that it is a third order, indicating that either the second or the fourth step must be rate determining. So either the second step or the fourth step must be the rate determining. Studies on the intermediate I. So studies on the intermediate I. So this intermediate they are talking about. So in I obtained by an alternative synthesis. So they synthesized in an alternative way. Have shown that K4 is about 4 times as large as K minus 3. So K4 is very large. This K4 is very large as compared to as K minus 3. This reverse process of this. So that about 80% of the intermediate goes on to the product. So most of the I goes to the product. This step is very fast. Understand this please one. This is most important, crucial one. That 80% of the intermediate I goes on to the product. It's a very fast compared to K minus 3. These reactions are faster than overall reaction under the same condition. So overall, this I will automatically go to this product. This reaction is very fast. This I will get to the product fast. So the second step must be rate controlling. So this is the conclusion. So this is the conclusion they are trying to make here, that the second step is the rate determining step, where the condensation between this PHCHO benzaldehyde and PHCOCH2 minus, this minus shouldn't be here. Okay, sorry. Just a second. So this condensation reaction is the rate determining step. So what we should follow from this mechanism study, this is the rate determining step, and this is experimentally proven. I will just color it and then leave it. So overall, if we go to the slide and discuss the question again, I will try to show it once again. So first they asked for what is the possible reaction mechanism. We showed there are 4 steps, individual steps. From the postulated mechanism, can we develop a kinetic expression? Yes, we did, matching with the experimental observation. So we did, and we had 2 equations which are similar. Then we got the another dilemma, which is the rate determining step. So from the experiment, from the intermediate they found that the last step is very fast compared to the other steps. So that's how we eliminate the last step as a rate determining step, and we got that the second step, where the PHCHO is getting attacked by the PHCO-CH2 minus, is the rate determining step. Experimental studies of this condensation reaction have revealed that it is third order, which we have been able to get the rate expression, right? So overall, this is our rate, this is our rate determining step, and we know the mechanism. So that was a thorough discussion on this condensation reaction. If we have any question, just let me know in the chat box. I will try to get it, and then I will move to the next question. Again, the next questions are also a little bit not tricky. Simple Curtin-Hammett principle. This is very. Oh, sorry, I have a numerical question. So it says that the pK of parachlorobenzoic acid is 3.98, that of benzoic acid is 4.19. What is sigma for PCl? PCl means parachlorobenzoic acid. Okay, don't misconfuse. So they are asking what is the sigma value. Now, if you follow the linear free energy relationship by ma'am class, so you will get it very easily. Let me do it here. Just a second, okay. It's a very easy question. All we need to do is something like this. Let me. No problem. So, what will be sigma? Sigma I am just writing here, right, like this. Okay. And sigma is log of two things, right? So I will have K for the parachloro part, and then divided by benzoic acid, that is capital K. Benzoic acid I am denoting as just capital H. So this is the equation. What we need, sigma equals to log of two constant, right? Now if I do it like this, again sigma will be log of it will be simple K, sorry, parachloro part, minus, just using log formula, sorry, log of K of H. I don't need this bracket. This part is clear. Now from the pK, what is the definition of pK? Minus log of K, right? So pK, please ignore the font like italics and other things, minus log of K. So this is the definition of pK which we have been given. Now what I will do, sigma equals to, what I will write, minus, so log of K PCl, which would be pK of parachloro part, and then since minus log of KH, it will be just the, so I will have a plus sign. I am considering minus log of pKh. So pKa of hydrogen part, benzoic acid part. Just a second. So we are almost done. So sigma equals to, now these values are given. Parachloro part, if I show the slides, 3.98, okay, and then 4.19, 3.98. So I have minus 3.98 and then plus, I forgot it, 4.19. 19, 4.19. Okay, 4.19. So that's how you get the, you just solve it and you get the sigma value. Please do it by your own, or you can follow the books. There are much 2 3 more questions on this kind of problem. So I hope this question is clear to you. That is done. I have 15 minutes. Okay, no problem. Now some again organic question. This was more of a physical part. So explain the following observation in light of Curtin-Hammett principle using reaction coordinate diagram. So this falls into the week 3 content, I think, based on ma'am's class. So I will explain the first reaction. It's very simple. It's an E2 elimination reaction, which I have 2 bromobutane. It is noted CH3, CH2, CHBr, and CH3, and NaOET. So it can give 3 possible products. So one of them is trans, that is Z. This is a major product, and then this cis butene, which is a minor product, and this terminal alkene, which is the 19%, which is the least amount is formed. Overall, this is the major product. We have been asked to using reaction coordinate diagram or potential energy diagram, and what about the Curtin-Hammett principle? How can we apply it? Whether it falls under that category or not. And then case 2 I will discuss later. Now let me do this question first. Just a second. Okay, this question is very easy. Someone is getting tried to attend or not? No problem. So we have 12 people. Some of you may left. No problem. So I'll come here and then clear the frame. Now, so this elimination reaction. So there is one condition that the eliminating group, the hydrogen and hydrogen and Br getting eliminated. So they should have anti-periplanarity arrangement. So this you know. So for example, I have Br and then I have hydrogens here. Actually there are 2 of them. So it will come here and it will go like this. So what we'll have, we can have this product, and we can have also basically cis trans product. Now if we consider the other case, that is hydrogens at this position, and this can come here and it can lead us to this terminal alkene. So this is the general mechanism. Now how do we explain this observation of 80% of this cis and trans and then 19%, though it is not the goal. So, which will be the major, this we have to explain. So this I will show in the slides. I am not going to draw. It is within my slides, so not a big deal. Now the 2-bromobutane, yes. So there you go. So 2-bromobutane can have multiple conformation, right? All conformations are in equilibrium. So they can have so many conformations, and all single bond can rotate. So if you see the conformation 1, which I have drawn, here the 2 methyl group which has a Gauss-Butane interaction. So these will have higher energy compared to this conformation 2, where the 2 methyl group are anti-orientation. Why we are considering these 2 conformation? Because within these 2 conformation we see there is the hydrogen and bromine anti-periplanarity arrangement. So this hydrogen at the right side and then this bromine. So these 2 are anti-periplanar. Here also in the left side we can see these 2 hydrogen and bromine are anti-periplanar. So both of this can go elimination reaction to give the corresponding product. So in case of this, where there is a Gauss-Butane interaction, we get the Z. And in case of anti things, conformation 2, where we can get the more favorable butene, 2E butene. So this, if I show the reaction energy diagram, so remember conformation 1 is less stable, so it is a higher energy. Conformation 2 is more stable. So this is the situation here. Just a second. Let me do it by myself or not. This is the situation here. So we have 2 conformation A and B, where A is the most stable conformation, and it is giving the most stable product. That is the most C is the most stable product, A and C. So this is the case conformation 2, which is stable and it is giving the most stable product. Whereas in the conformation 1, which is unstable, has a higher, less favorable, higher energy, and it is giving this product. So this is the situation here. So we have someone, let me join. Okay, so I hope this point is clear, but let me show it also so you will feel for it. Otherwise, it doesn't make sense. So I have some time. Let me show. So we have two conformation. Remember, one with a higher energy, which is a Gauss-Butene interaction, and another is a no Gauss-Butene interaction, and methyl groups are trans. So it has a lower energy. Imagine in the y-axis there is a. So if I name it, what was the conformation I showed? Conformation 1 will be higher energy. So I will put as here conformation 1 and then conformation 2. So these are the situation. It has a higher energy, it has a lower energy. Furthermore, so it has a low energy transition state, and the product is also much more stable. So let's say product is here, and conformation 1 gives a less stable product because the methyl group persists, so there will be steric interaction. So product will be also high energy. So PDT1 and then PDT2. So this is the situation. What about the transition state? How will I draw? So this conformation 1 has a high barrier. So let me put it here. Sorry, just a second. Conformation was a little high barrier, and conformation 2 has a low barrier. So all this point will be very clear. Just a second, give me some second. Document settings, and all I need to do is drawing. Let me make it 4. So I will just draw some lines, and it will give you the familiar potential energy diagram. So conformation 2 followed by transition state, it is giving the our product 2, right? So this part is the transition state. I will make it little nice. And conformation 1, which is high energy, which is also a high energy transition state, and it is giving us the low energy high energy product, sorry. So this is the situation, and also we need this equilibrium. So conformation 1 and conformation 2 is in equilibrium, but the equilibrium, so it will have a corresponding transition state, right? So it should be much lower actually. This can undergo rapid equilibrium, and this is the conformation and transition state. So this is the situation. Okay, so what I can do, this is just qualitative picture, okay, so don't take it too seriously. And yeah, so overall it will look like this. Conformation 1, which has a Gaussian interaction, has a higher energy transition state to give us the product with a little bit high energy. So this is the cis product. So cis. So it is a minor product, and here it is the major product. Okay. So in terms of Curtin-Hammett principle, here the the conformation which is more stable is giving the major product. So here the conclusion is the conformation which is more stable, like conformation 2 is more stable, no Gauss-Butene interaction, it has a low energy transition state, and it will give us the major product. So this is the typical Curtin-Hammett situation. So this is the one type of situation where major conformation is giving the major product. Now come to the second question. Second question is little bit different here. I will try to show it here in this. So we have little time. So here you see this case 2 where I have given methyl chloride cannot eliminate is written. So you see this conformation which is undergo ring flipping and giving this less stable conformation. While less stable conformation, this CH-Me2 group is in axial position. So the more stable conformation, so at the left side we have more stable conformation, but since it doesn't have any hydrogen which is anti-periplanar, so these adjacent hydrogens are not anti-periplanar to this chlorine atom, so it cannot eliminate. Whereas the high energy conformation, this is high energy conformation, the CH-Me2 group is in axial position, it can eliminate. due to the presence of an hydrogen which is anti-repellent to this chlorine, and this can give the only this product. So here situation is little bit different. In the earlier case, the conformation which is more stable is giving the major product. So this is the case. But here the more stable conformation is not giving any product, whereas the less stable conformation, it will go and it will give the major product. Overall, the situation will look like this. Let me explain this diagram. See, A and B are two conformation. A cannot eliminate. It has a high energy barrier. Transition state is very high. No hydrogen is anti-particular. Whereas in case of B, though it is unstable, less stable. Though it is less stable compared to conformation A, it has a low energy transition state. So overall, it will go and forms the product. So any conformation, once B is undergoing reaction, the A will transform. A will undergo conformational change to form B. This energy is very less compared to the transitions energy here, and it will form the products. So the overall conclusion is that it may be the case where the less stable conformation, again less stable conformation, can give the major products. So both situation I have shown, where the more stable conformation giving the major product, also the less stable conformation can also give the major products depending upon the energy of the transition state and the conformation. And I would like to say thank you to all of you. And if you have any doubt or question, let me know. Then I can stop it. Thank you. I was constantly speaking. Uh, Let me know your thoughts. If you have any question, just let me know. And you can also tell me if the questions were, too easy or too tough, and I will try to adjust accordingly. Okay, it seems there is no question. Uh, are the slides available in Jamboard? Uh, slides will be available. I will share you. The links will be shared for presentation slide, and elsewhere. I think the NPTEL team, like IIT Madras team, they will share with you, and you can see the video again in YouTube also. So YouTube link of this lecture and the presentations will be available to you. Don't worry about that.
Sir, excuse me, sir.
Hmm.
Actually, in this Curtin-Hammett principle,
Hmm.
the stability of the conformer
Hmm.
will not give idea about kinetic control or thermodynamic control.
Yes.
So we cannot say which product is kinetic and which product is thermodynamic.
No, no, no. So basically, the it is not the conformation, but rather the transition state of the two sides will determine things.
Okay, transition state energy.
Yes, mainly the transition states energy will determine. Sometimes low energy conformation can give the major product. Sometimes high energy conformation can give the major products, depending upon the transition states.
So in the previous slide, the previous problem you showed me, no sir, you showed to us
Huh.
at which condition conformer A will give maximum product, at which condition conformer B will give maximum product.
Uh, so condition in terms of your temperature dependency you are asking, right?
Temperature dependency.
See here it is this reaction, it's an elimination reaction, and this two, I think this conformation two will be the most stable conformation. See the equilibrium sign,
Oh, yes, sir.
80% will be in the conformation two. There is no Gauss-Button interaction, so it will be the major product. If you want to have more elimination product, it is better to use high temperature.
High temperature. Okay,
Huh.
sir. Thank you, sir. Thank you, sir.
Okay. Okay, then I will leave, and thank you guys for staying.
Thank you, sir. Very kind of you, sir.
Okay, thank you.